Okay. Yep. It's over, John?
All of the above shouting.
Yeah.
Right, welcome back, everyone. One more talk for lunch. So it's a pleasure to welcome Scott McCue from halfway across the world. So Scott will give a talk on singularities of Burgers equation in the complex plane. Thanks.
Thanks, Phil. And thanks, Chris, also, for allowing me to speak in this workshop. So this work on Burgers equation is done in collaboration with a student, Daniel Vanden Heuvel. And Daniel and I, we're at Queensland University of Technology, which is in the city of Brisbane, where there is a cricket game on right now that John's been watching, in Australia. And this is also with Chris Lustry and John King, who are both a part of this program, and perhaps in this room I can see Chris. Okay, so I'm just going to say that this work is done, or at least was started as part of Daniel's third-year undergraduate project last year. And so perhaps, perhaps some of these themes will be a little bit more gentle than some others in the workshop. Okay. Okay, so here's Burgers equation. So Burgers equation is very well known nonlinear PDE that exhibits competition between wave steepening that comes from this nonlinear advection with smoothing that comes from the linear diffusion. So I guess in terms of applications, you might imagine that Burgers equation could be considered a toy model for traffic flow, at least in an undergraduate class, or as some sort of crude version of Navier-Stokes equations in 1D. Now, I'm not sure how applicable that really is, and regardless, I'm not going to talk about any applications in this seminar anyway. So I've just left this mu in the equation. When mu is 0, we have what you might call inviscid Burgers. In that case, the wave steepening keeps going until a shock forms. So this is a type of blow up, which is finite time blow up in the derivative of the solution. And then so if say if mu is greater than 0, in full viscous Burgers, any wave steepening is eventually overwhelmed by the diffusion. Okay, so it's very well known that Burgers equation has an exact solution here that you get via the Cole-Hopf transformation, which basically linearizes the thing and turns it into the linear heat equation. So let's say for an initial condition like this, 1 on 1 plus x squared, which is an initial condition that I'll be using in this seminar, then here are some solutions to Burgers equation that you could get, if you like, easily enough from the exact solution or just numerically. So here's the initial condition, this sort of a hump. So this is an example for small mu. This is mu is 0.1. This is an example for larger mu. Mu is 1. For the smaller mu case, maybe you can see that these sort of profiles steepen as time increases. And for this larger value of mu, mu is 1, the solution just smooths out initially. I've also shown here in red, if you can see this dashed curve, this is the solution for mu is 0, the inviscid Burgers solution at the time at which a shock forms. So you can see here that for mu positive, that the solution continues through nicely past what would be the shock time. And so the solutions then they exist globally in time. Okay, so this sort of simple observation at this level is that there seems to be some sort of borderline case mu tilde. So for small mu less than mu tilde, the solutions begin to steepen and then smooth off. But for larger mu, they just smooth off. And I'll come back to this point later. Okay, so now moving into the complex plane, we'll just briefly think about this inviscid Burgers equation, the mu is 0 case. So in that case, there's these branch point singularities that, say, complex conjugate pair that evolve towards the real axis and then hit the real axis at finite time at the time at which the shock forms. So if you like, you might interpret that as the reason for the shock forming as being the branch point singularity hitting the axis. Okay, you can do this. Well, this is an undergraduate thing, inviscid Burgers with your method of characteristics, so you can work out that shock time for that initial condition from the previous slide. Okay, now, so I'm in the complex plane. For mu greater than 0, well, then what happens is whatever singularities there are, they might head towards the axis initially, or they might not, but they don't hit the axis. So if you like, you might interpret that as being the reason for there being no blow up in that case. Okay, now all of this, everything that I've just said is so very well known. And okay, so for example, there's these papers that are of particular interest where these authors considered these initial conditions, they're very similar initial conditions. They're both odd. And so while much of this stuff is really quite complicated, at least to some extent the analysis is simplified because the singularities must lie on the imaginary axis for these initial conditions. And another point to make about these is that these initial conditions are entire functions. So for these cases, the singularities must come in from infinity, regardless of mu, and then they turn around and go away again. They get afraid of the real axis. So, okay, now with that in mind, we're going to use this initial condition. It's the one that I mentioned before, 1 on 1 plus x squared. Okay, so now this seems like the sort of most natural or the simplest initial condition that has one simple pole in each of the upper and lower half planes. And they're located at a nice place, I and minus I. So now, okay, so for whatever it's worth then, some of the details will be more complicated with this initial condition because the singularities are no longer constrained to be on the imaginary axis, then can move in the plane in any direction. And also, I guess what we're really interested in is that we want to see singularities being born at the simple pole at t is equal to 0. And maybe some of them will move towards the real axis, or maybe some of them won't. And at least to that extent, this behaviour might be slightly more interesting than part of the very complicated analysis in those papers. Okay, so I should say that this very problem then, Burgers equation with this initial condition, has been studied in some detail by these characters who you may know: Chapman, Howes, King, Alder, Dehus. So that's all very detailed, but one of the focuses of that, or the main focus of their study, is the limit that mu goes to 0, whereas we are more interested in, say, mu is of order 1. So I'd like to think that there's some complementing going on there with an E, not an I. Okay, so maybe one line summary of what the goal is, just to explore the singularities and also to use a variety of techniques. Some of them will rely on Burgers' equation being so nice, but also some others that don't. So with a view to, in the future, or separately, doing similar things for other PDEs which don't have for exact solutions and so on. And also sort of make some comments about how some of this stuff in the complex plane affects the real solution. Okay. So I'm going to plot some complex functions, and I just wanted to put this up here. Here is the initial condition plotted here in this analytical landscape. So just to get your bearings there, it's the modulus that you're seeing in the surface of the function. But the colour in here in this phase portrait, which is like a plan view really, the colour is sort of given by this colour wheel. So it indicates the phase. So you can do a couple of things with this. For example, locally a simple zero will look like this colour wheel, at least up to a rotation. And locally a simple pole will look like the colour wheel, but with the colours in the other direction. So then, say, if you didn't know that there was a simple pole there, you could look at the phase diagram and sort of track the colour as you go round. You go round once, it's a simple pole because the colour's going in the other way. And you might remember, for example, like that red is real and positive, and maybe if you've got bad memory, that'll do. Okay, so here are some solutions to Burgers' equation that you can plot with that exact solution that I put up before. And with this initial condition, this is the one I'll be using now for the rest of this seminar. So there's a bit on this slide. So these are at different times, 0.1, 0.5, 1, and some other time, which would have been the shock time, but just say another time. In each case, there's the phase portrait and this analytical landscape. I'm only plotting the upper half plane because it's the same thing's happening in the lower half plane. And also with the upper half plane, then I can also plot the solution itself on the real line here. So you can see that the solution here for this case, which is the smaller value of mu, well, you can't really see, but you can imagine that it's sort of steepening up a bit on the real line. Okay, just remember red was real and positive, so you can see the phases red where it should be. Here the black dot is the point z is I. And you can see that, well, it appears that the singularities, or that, okay, I'm going to say these are singularities. You can kind of see the spikes here. You can see that they're sort of emerging from this point z is I, or at least it looks like they are. So this is to remind me of what to say. So just do a check. Okay, so I've mentioned the phase. So poles, so I could look at this phase diagram and guess that they're poles just from the colour, tracking the colour wheel. You'd have to zoom in to do that, and you'll have to trust me. Also, each one of these poles has got an associated friend where there's a simple zero that's close to it. So there's sort of a pole and then a zero, pole and a zero, pole and a zero, and so on. Okay, so the hypothesis here is that there's a countably infinite number of these singularities that are born at this point, z is I, and that's the point at which the initial condition has the simple pole. You can see they're aligning up in an array here, sort of coming out at sort of roughly 45 degrees. They're separated. You can see the separation distance seems to be increasing with time and also decreasing as you go further up. So another point I'll come back to briefly is just looking at the far field. If I want to go this way up the far field, so this is up the imaginary axis, it seems like the solution is growing up. It's not decaying off, so it doesn't seem to look anything like the initial condition in that direction. Okay, the last thing is this important thing I want to talk about in some detail is the closest pole, which is given here by the arrow. So here is, for this value, there's a small value of mu. The closest pole seems to be sort of slightly underneath z is I and to the right. And it's moving slightly down. You can't really see that. It's sort of heading along, but sort of heading down towards the real axis a little. There it is there. So I'll just do that one more time, but this time with the larger value of mu. Mu is 1. And okay, here you can see these solutions on the real line. It's hard to tell, but remember from before that this is one of the cases where the profile just smooths off initially. It doesn't steepen and then smooth. Okay, so many of the features are the same as before, the array of poles and each pole having a friend of which is as simple 0 and so on. But one thing that's different, if we look at the closest pole here, which is given by this white arrow, in this case, for the larger value of mu, the closest pole to the real axis is moving away initially. So it's just sort of moving up. Okay. So what are these singularities? Well, I'm calling them, I can see that they look like simple poles from the plot, but you could be tricked by that anyway. I think it's fairly easy to see, at least a leading order, that these singularities are simple poles. And it is known that they're simple poles, but I'm just making the point that you could very simply just back of envelope look for the type of singularities for which Burgers' equation can give rise to, and that you can just see that there's a leading order balance between these two terms, and that gives you that it's a simple pole, which is this power 1. Also gives you the strength of the pole, so that all of these singularities of Burgers' equation are given by this very simple form. So we can see that every one of these singularities in those plots now must be simple poles like this. So perhaps at this point you think, well, it appears there are infinitely many simple poles that are born at t is equal to 0 at z is I, and again at minus I, but I'll just think about the upper half plane. And they seem to align themselves in an array in each quadrant of these two quadrants. The actual direction that the closest singularity seems to move depends on mu. If it's small, then it seems to head towards the real axis. If it's larger, then it's moving away. And one of the things we want to do is sort of get more information out of this, or describe some of this with pen and paper and also with a computer. So then I think that I'll talk for a number of slides out of my 23. I can't remember, but I'm up to 7, probably up to about here, on the small time limit that we're interested in, because we're keen to learn about how these poles are created and their initial motion and so on. So you might say look for a naive type of expansion in t for small time, and that's relatively straightforward. You can get, say, u1 in terms of u0 and u2 in terms of u1 and so on. Of course, you see that you're differentiating twice to get from one to the next, and differentiating twice to get from one to the next. So that you get something like this, and it doesn't really matter so much that's the leading order bit, that's the initial condition. Here's some stuff, but I'll just sort of write in blue if you want to write it like a rational function. You can see what the effect of the repeated differentiation is to sort of have 1 plus x squared to the 1 and to the 3 and to the 5 and so on. So this type of approximation is probably very good, except where it isn't. And that's going to be near z is I, of course, because here the initial condition is sort of got this 1 on Z, or behaviour. And then because of the repeated differentiation, U1 has got 1 on Z minus I to the 3, and U2 is Z minus I to the 5. And so no matter how small t is, it's multiplied by something that's getting bigger as you're getting closer into the singularity Z is I. So eventually the whole series must break down. So it breaks down when, say, for example, that thing is the same order as t by that thing, which I've just written here. So it suggests an inner variable xi, which is you get from this expression. So I'm going to use xi a lot, and this, you should remember that xi is the inner variable and it's centered at z as I. So the origin in xi plane is you're looking at the near z is I in the original variable. Okay, so your inner variable is this that I just said, and that if you like, I mean this is going a bit painfully slow, but you can write your outer, write down the far field of, or rewrite that inner limit in this outer variable, so that suggests to you what sort of form the inner solution should look like. It should be u is 1 on t to the half by some function of xi and t. And I've just written that here. And then you can now write out an expansion for phi. And the form here with t to the half and t is suggested by this matching out to the outer problem. So it turns out we get this an ODE for the inner problem, and this is an interesting ODE that we deal with in some detail. It's sort of got this, this nonlinearity from the advection term. Now we match out, we sort of pick off this term here. Well, this will be our matching condition here for phi 1 minus I on 2xi. But this direction is important. We should match down because we're at z as I. We want to match down to the real axis. Well, in this instance, well, it can be, yes. I'll effectively mention that in a moment. Yeah. But say naively in the order that I thought about it, we should match down, and it can be at any angle, but also even further up, as I'll mention. Now, we started with Burgers' equation, so you wouldn't be surprised that this, which is effectively another version of it, has an exact solution. So you can integrate once explicitly, and then it's a Riccardi equation, which you can solve. And so these here are parabolic cylinder functions, so this looks nice enough. So there's the exact solution to this inner problem. Now, because we've got the exact solution, I can plot that, or Daniel can plot it anyway. And so these four are the exact solution to the inner problem plotted, and these four are the exact solution to full Burgers' equation that I'd put up in the first or second slide at very small times, like t to the minus 6 or something. Okay. And also rescaled to be zoomed in, with a magnifying glass to match the scale of the inner problem. And the agreement is remarkably good. It's quite surprising. So now you can see from an inner perspective, this is self-similar, really. You can see these, here we'll do, these poles and how they align very close now, or as close as you like, to z as I, because we can take this this solution and sort of squeeze it in by taking smaller and smaller time. What's the difference here? Well, this is a small 0.1, mu is 0.1, 0.5, 1, and 2. So what's there to say? Okay, so the first point is that, okay, well, all of these singularities, you can see where they are relative to the origin in xi plane, and therefore in the z axis, they should go like I plus t to the half by wherever they are. Another point is the location of this. We can look at the location of this closest singularity, and that we're wondering whether it's in the lower half plane now or not, because remember the origin for xi is fixed to z as I. And okay, these dots and the black curves come from approximation that I'm going to put up later. Okay, so now I might want to move a bit more quickly through some of this. So this is the ODE that I'd put up before, in that, okay, I'm just reminding you once again that the origin in xi is z as I, and that here I'd said we want to match down, so directly down xi down to minus I infinity. Okay, so one point is we could get more terms. Here's one more. We could get as many as we like, really. You can do WKB on this and sort of linearize around this boundary, around this far field condition, and you see that there's this exponential that appears with, it's like e to the, xi to the minus I on 2 mu, e to the minus 6i squared on 4 mu. Okay, so this sort of tells you really that the Stokes line will be where this singulant is real and positive, which will then be the real axis. And also that, okay, well this thing will have a 0 in front of it in the lower half plane, so it won't appear in the lower half plane. It will be switched on as you go and sort of go through the Stokes lines, which will be the real axis. And we'll keep going up to the anti-Stokes lines, which will be sort of at 45 degrees. So this is really the sector for which that boundary condition applies. So you might ask, sort of, what happens past the anti-Stokes lines? Would be a normal question to ask, I think, and also whether you can describe the location of the singularities, except that here we're going to cheat a bit because we've got an exact solution to Burgers' equation, but still it's an interesting question. Okay, so as I just mentioned, that I can actually write down the far field of the exact solution by just getting out the digital library of mathematical functions or something, looking up parabolic cylinder functions, and that will tell me that this thing here, phi naught, this is the leading order term in the inner problem. It goes like the thing I know that it goes like all the way up to these anti-Stokes lines. And you can even write down behaviour on the anti-Stokes lines. And further, even, you can see that it grows like xi. So what is this? This is sort of interesting, this thing that it grows like xi, at least to me, it implies that the solution does not match out to the initial condition in all directions. In fact, we saw that before. I tried to highlight that if you look at the numerical solution, as you go up the imaginary axis, the solution grows. I mean, if you're on the outer, then it feels like U has this form of effectively Z on T in the limit that you go back into that singularity. So, I mean, this and other observations make it clear that the solution to Burgers' equation with an initial condition like this doesn't actually approach the initial condition everywhere in the limit when you go back onto Z, back onto T is equal to 0. So this sort of observation might be obvious to some people here, but it sort of tricked me up for a while. Okay. I mean, just because we can use the exact solution to locate where these singularities are. So just for example, very briefly, the exact solution had this parabolic cylinder function on the denominator, so I want to see where that's 0. And its far field behaviour is something multiplied by 1 plus something. So I want the 1 plus something to be 0. But the something has this e to the minus 6i squared on 4 mu bit, so this is going to be exponentially small below the anti-Stokes line and large above. So there's going to be some sweet spot where you sort of get increasingly close to the anti-Stokes line as you get further away. So you sort of get a little bit of it, a little taste of the exponential to match this to get -1 somehow. So putting aside any of the detail, you can then get a little formula for the theta in terms of just say this modulus of xi, and that's the black curve that I'd put up before. And then you've got some transcendental equation that leads to this order, which is not totally asymptotic because I left a 1 there, but that'll give you the actual points in the limit. Or, simplified version of this is that the distance seems to go like 8n mu pi, or at least the square, and the spacing between them goes at 1 on root n, which is consistent at least with this observation that they get close together. So I've had to squash this figure in here, but if you have a look at this example, mu is 0.5. These approximations are quite good. They're even sort of smashing it from the beginning, which is quite good. Here for mu is 1, not so much for this one, but still. Okay, I've got 3 slides of a digression that I think I will go through more quickly. I'm not sure how interesting this is, but we can observe this exponential switching on across the Stokes line in what I would say is the usual way. Now, amateurs like me, I like epsilon, so I just sort of do this transformation. It's slightly embarrassing to create an epsilon there, so I can take the limit epsilon goes to 0. In this case, it's explicit that epsilon here is sort of multiplying the highest order term here. But you don't need to do this. You can just do it in the far field. In the usual way, I write out phi naught in terms of this, what would be a divergent expansion, and I can just start writing down terms. The Fn will be this form 1 on xi to the 2n plus 1, and you can track the relationship between Fn and the important bits, at least for large n. So we're going to use this many terms, but no more. Oh. Okay, you can sort of solve this thing asymptotically, and you can find that Fn looks like what you think it should look like, this gamma, this sort of factorial over power divergence, where this chi is that function, which is the singulant. And you can get everything from this. You can get this function a, which is the other side of the minus I on 2 mu, and even the constant out the front, and the gamma, which turns out to be that number. Or if you like, you could do it again, but another way, which is just to take the ODE and say that you guess that the late terms in the expansion should look like what you know they should look like, and then put that in, and then solve one at a time for each of these components. For example, to leading order in 1 on chi to the n plus gamma plus 1 gives you what turns out to be the singulant. And then to the next order, you get this a, but in this case you don't get the constant. If you want gamma, you sort of look at the form of the solution, and you go back to n as 0 and just sort of match up to make sure that they've got the right strength. The singularity has the right strength. And if I want this sort of Stokes constant thing, I can sort of look at the local behaviour, and I get it in a similar way to before. Okay, this is the third of my 3 digression slides, which is just to say, okay, well, we can truncate this series, of course, which we want to do that optimally, but we'll have a remainder. So if I write this and put it into the original ODE, then I get an ODE for the remainder. And the right-hand side's got stuff that's all missing, but all I need is this first term, because I want to truncate when epsilon goes to 0 for large n, capital N. So this will be the leading order bit. This capital N goes to infinity. Okay, I know capital N. I know capital F. Sorry, I know Fn now. I know the size of it, so I can just chuck it in there. So the right-hand side looks like that thing. And then in the usual way, I want to truncate optimally, so I want these 2 terms, whatever they are, successive terms, to be the same size, and that tells me what I can choose for n, the optimal truncation point. It's not an integer, so I make it 1 by adding on some number. Then really I take this, I know that I want to switch on this bit here, multiply it by some c of xi, and plug it back into the ODE to see that this derivative to c dxi is exponentially small here. If you look at this maroon bit, would be very familiar if you've done all this like this. It's a recipe, really. It's exponentially small because we've got this minus rho squared over epsilon squared, except wherein it isn't, which is when this bit in brackets is equal to 0, and that's at theta is 0 and pi. So these are telling you that there's Stokes lines there. So this is sort of crying out to be rescaled, and I'll just do one of these very briefly, which is to say theta is 0. And so the rescaled version of this, when I sweep around and in an angular direction, where this angle here is theta, gives me dc d theta. The scaled version is e to the minus theta squared. And that's the error function, essentially. So I switch on this bit here, leaving out some of the details. But this is sort of precisely what you would expect anyway. OK, so that's the digression over. So if I've still got anyone's attention, I've got 10 minutes, I think. OK, so just for fun, let's sort of go back and look at this nearest singularity, just to remind you that if there was a singularity in xi plane, let's say xi naught, then in the z plane, that singularity goes like I plus t to the half xi naught. I can look at that inner problem, and the inner problem tells me that there's a special case for mu, say 0.1468, where the closest singularity to the real axis is, for mu less than that, is on the lower half plane. For mu greater than that, it's on the upper half plane. So this is telling me whether or not the closest singularity to the real axis in z moves towards the real z axis or away. Initially, this is. And so that's interesting. So I want to track this closest singularity. I can do it a few different ways. One way was just to use the method of steepest descents. And so very quickly, if you remember from before, there's this exact solution. I want this thing here to be 0. I can use steepest descents then. So there'll be cases, say, if you think for a fixed z and t, you'll be in the s plane. And so for one fixed z and t in the s plane, there can be, say, up to 3 of these saddles. So you want 2 of the saddles to give the same size, to be at the same height, to give the same, to possibly give the same contribution so that they can cancel each other out to give 0. And so this is ultimately is a sort of numerical exercise to find one of these and just to move a little bit and find them again. And another strategy which we just employed is to use this AAA algorithm, which is a numerical scheme to write down some rational approximation to the function. And this, as an output, gives you, for example, the closest singularity. So with those 3 methods, this is the evolution of the closest singularity for 3 different values of mu. Small, that borderline case, and larger. And each of the 3 different methods is sort of collapsing to each other, so that's nice. And here, this distance of the singularity to the real axis versus time looks very similar. Okay, so I did promise to say something about what happens to the real line. Well, if you just look at solutions, numerical solutions on the real line, now, I've already mentioned this, that for very small mu, the solutions steepen and then smooth. For larger mu, they just smooth off. It seems like there's an analogy here with the direction of the closest singularity, which also has a cutoff value for mu. So for the real solution, here I've plotted the maximum slope, and this is mu is 0 in viscid burgers. The maximum slope just slows up in finite time. But for small mu, the maximum slope increases, but then ultimately reaches a maximum and comes down. For very large mu, it just sort of goes down because it's just smoothing. And so there is this borderline case here somewhere. So it turns out that numerically for the real problem with the real line, this borderline case is something like mu is 0.1458, so to the extent at least that we can approximate to that many decimal places. And that, remember, the borderline for the direction of the closest singularity was 0.1468 or something. I mean, they're very close. They're sort of out by a 3rd decimal place. Now, just to sort of make the observation that this is an interesting link, but I mean, to what extent? I mean, I'm not necessarily claiming that they're the same number, but it's at least interesting that they're very close. Okay, I think I better move on a bit. Okay, we could also, another point of interest could be the time at which the real solution, if it starts to steepen, then it smooths off. And also see if there's a link between this other idea, the closer singularity, which gets closer to the real axis, eventually must turn around because it doesn't hit the real axis. So you can sort of track these maxima here for one and the maxima for the other and try to relate them. They don't relate as closely as this other phenomenon. But anyway, I see I've got a minute. Well, I mean, eventually, regardless of mu, all the solutions smooth off and the closest singularity moves away from the real axis. So we could plot this solution in the complex plane for 4 large values of time, and you can see, well, if you're paying attention, the scale's different here. But the structure looks very similar to small time. It's just that you're on a different scale. So this looks like there's a similarity solution from, say, my third year class or your third year class, which looks like this. You match back not to the initial condition, but at least to the mass of the initial condition. So in the original Z variable, this long time solution looks like this. And that's nice because we can also take that and plot that in the complex plane. And so something I just very quickly notice is that I mentioned before there's these poles and zeros, they're friends. Well, they seem to move further apart as t goes to infinity. In fact, I think when you look at the effectively t is equal to infinity solution, they've moved right away. Okay, that's just some comparison, which is good. And here is some other. Okay, here are these pole location, but now for large time, and I can do the same thing as before. It's much easier in this case, actually. I can get a formula for that's the black curve, which is this, and that I can pick off the white dots with this formula here, and they match up very nicely, even for small, even close to the axis. Okay, so that's it. Okay, so the summary is, okay, lots of people study Burgers equations. I'm not claiming that hasn't been studied before. In particular, these wise characters who use this initial condition, but just as a point of difference that their focus was on mu goes to 0, whereas much of what I've been talking about applies for mu as order 1. The idea, it's just a hypothesis, of course, is just that there are countably infinite number of these simple poles that emerge from Z as I. They align themselves in these arrays that head off and get closer to the anti-Stokes lines. I think this inner problem is quite interesting and that there's heaps going on there. You can look at the closest singularity, far-field behaviour, and so on. Try to locate the poles. I spent some time talking about the closest pole and made some effort to relate that to the real axis, to the real solution. Okay, so the final point here is just that, of course, Burgers equation is nice for lots of reasons, but some of these approaches would apply for more complicated or different PDEs that don't have exact solutions. And so that's part of the motivation for doing this. And one more. Oh, okay, so this is thanks to people. This is on the archive. This is Daniel. That's me. Daniel is taller than me. And this is Chris and John, me, as recently as last night. And that's my Twitter handle. And that is it. Same shirt as Daniel? No, this is a short sleeve shirt, John. This is a long sleeve shirt. See that? And this I was much younger then. It was about 2 or 3 weeks ago. Maybe.
Burgers, what
Yes.
The only difference is that if you have complex, you can reach poles can reach real line in a finite time, according to the real case. But otherwise, it's very similar. So I just trying to get more motivation here. Basically, all the results which you obtain here, you can easily get from pole hop, which I introduced 2001. For example, all these results about distance to real line of closest pole. And my understanding also works. If you have generic pole, right, when in infinite small time, it will produce, I mean, in infinite small time, it will go to countable set of poles. You got such result, which you can get just from pole. Of course, there are solutions with the number of poles which comes up. So,
Okay.
so what's the motivation? Because
Well,
you can go everything from pole. I understand that, and you want to learn technique for other PDEs, so what's the motivation?
Okay, well, one, just briefly at the beginning, I have seen Andre Weidemann do something with complex initial conditions, but for the most part I avoided that. I'm not so sure you can get everything from Kohl-Hopf. We didn't. Even just numerically evaluating that exact solution is quite difficult. If you imagine in the plane, for 3 reasons, small time, small mu, or close to the singularity, you get highly oscillatory integrals. So that's one of the challenges. Well, maybe you can, for mu as order 1, get information about the closest pole easily from there, but we didn't.
Well,
and okay. Yep. Okay. And so I think like the more generally the motivation is a mix. It's to study a nice problem for which you get stuff for free, and that's burgers. But also to, what I would say is to try to use or develop or apply some techniques that would apply to other PDEs. So, I mean, to the extent to which that's true, I'm not sure we could talk about that, but that really is the motivation.
Can you explain why you cannot use the exact equation to obtain the result? What is the
Okay, well, look, you can take, for example, the small time limit of the integrals using the steepest descent, but you get the same as what you get just from analysing the ODE directly. The ODE goes back to 0, you end up just with the initial condition, and so on. So, I mean, that's a starting point. Then you can look if at the inner region around here, you would work, reasonably hard to turn that integral into the type for which you could expand and so on. But it's easier just to use the ODE directly in that case. So I'm not sure that you can't use Kohl-Hopf, but because I'm trying to play both games at once and so that I win no matter what I say, I want to partly use the exact solution, but I also want to partly not use it, because for another PDE where I don't have Kohl-Hopf, I can just analyse the ODE, the PDE, and then an ODE for the inner problem directly. And so that's of interest to see whether it works in this case. But I'm not so sure that it is such a useful exact solution anyway. Well, for whatever it's worth, we just found it easier much of the time to pretend it didn't exist. Except when we're plotting nice solutions, of course.
Yeah, the technique that you elucidated as far as small time expansion and seeing where it goes bad and then discovering similarity solution, approximate similarity solution. This kind of thing has been done before in quite complicated problems. So you probably, I'm not sure if you're aware of it. Are you?
The daughter singularities, you mean?
Yeah.
Or just not that complicated?
No, even the Healy-Shaw or
Yeah.
the Kelvin-Helmholtz or the Rayleigh-Taylor this
Well,
kind of thing.
Healy
has-
Shaw, yes.
yeah, yeah.
Oh, well, I mean, you know, to some extent, this is a sort of a gentle. This is meant to be a gentle little seminar here, not Healy Shaw daughter singularities, which I am aware of, but I have to confess I don't totally understand.
So, as time tended to zero, you essentially had singularities moving towards the origin. There's similar problems, such as in ODEs, for which singularities will cluster and they'll form a new singularity with a different strength, such as the limiting Stokes wave. So it'd be interesting to see whether it could deal with problems like that as well.
Well, I just think that in this case, Burgers tells you in advance what can happen, and that's that you only get simple poles with that particular strength. But for something else that's not so constrained like Burgers in that sense, then yeah, that would be quite interesting.
But the initial condition has a different strength.
What the initial condition does.
It's still a simple pole, but it's a different strength.
What is? For those other problems.
No, in Burgers, your initial condition has a different strength to all your other poles.
No, in this case, oh, different strength, sure. But,
So
okay.
it's not, are your poles coming down to approximate that different strength instead of it just being a different type of singularity?
No, the poles that are developed in Burgers' equation are movable poles, and they are all constrained to be of a particular nature, simple poles and so on. The initial condition is something you specify. You can specify that to be anything. But then the poles that develop and move are predicated by the equation.
I mean, if you have initial condition that doesn't have simple poles, some other singularity, then it appears like for small time you have singularities that aren't simple poles, but then you rescale about them and you'll get a new,
Do you agree that
you know,
in
to
infinite small time, any initial condition just go to set of poles, right? You agree with that?
yeah, I think
But
so.
since it's simple situation groups and our PDEs, it might be really different because we really enjoy whole pole. So it's kind of picture really simple. I mean,
Very simple.
it's a dialogue.
Nalini?
I just wanted to say that this discussion really points to very interesting examples that you could also tackle by the methods that you talked about. For example, the KDV. The KDV also has movable poles. They are different to the Burgers poles. It all comes from the Punlevay property of these equations, which is what I've studied in the past. And so it would be interesting, for example, to see if there's a parameter in the KDV that you can tune to bring those poles down to the real axis, for example, that affects particular applications of the KDV. I think that would be a really nice problem to tackle.
Well, I think in the same study, Andre Weideman's paper that I'm remembering, well, there's a couple of them, but he also looks at KDV, and the themes are very similar, so yeah. So I'm sure that lots of people have looked at that. Yeah.
I'm just saying it would be interesting to see how your method
Yeah.
No, we look on that a little bit of KDV. It's much more complicated with poles with KDV than from the complex surface.
from the Punlevay property point of view, it's just double multiple
We look for more generally. The condition with some poles and then how they develop or some branch not showing up.
No, there's no movable branches. It's a Punlevay property.
No,
No branches.
you're talking about particular solutions, right?
No.
Engineering condition.
Engineering.
So let's thank Scott for a wonderful talk. This is a very inspiring talk. And then let's take some of these discussions to lunch.